All right, so we're back again with velocity. This is velocity part 2. I was making the video yesterday and I knew there was something else I wanted to talk about, and then I realized, I wanted to kind of make a mention of this other kind of twist on velocity with our graphs. And so I thought, well, it's more complicated maybe than what it would seem to be in 30 seconds. So I went ahead and made a second video for tonight to watch as a kind of continuation. We have also a lot of in-class activities that we're working on right now. So we've got a number of things that we'll be hitting within these two videos. So hopefully this will help you understand some more of those problems and what we're really doing when we're running our cars down ramps and we're taking and counting dots and changing dots of position into velocity, etc. So on to velocity part 2. I like to look at, and this is kind of our other end, and I'm going to use that word calculus, but again, it's not a scary word, and I know that some of you have never taken calculus, some of you are going to take calculus, but we just like to look at things underneath a curve, like an area under a curve. And so we look at this and we say, well, what does this represent? Now, I have a graph, and my graph is velocity versus time. So in other words, I've got velocity and time, and I can look at it in terms of kind of like finding area of a shape. So in particular, I might take this spot right here. So from this point to this point, we can analyze our graph and say, well, what's going on with our car or whatever it is that's moving? And it seems to me like we're driving along here at 8 meters per second, and we're not changing our speed. So in other words, our velocity is constant. Now I'm going to go back to our original relationship that said distance is equal to velocity times time. That's the number one equation on our board up there. And so if I look at this, I have a velocity, and I know for how long that velocity is going to be running. So in other words, the product of these two gives us the distance. Okay, so now we're thinking the product of these two, a velocity times a time, will give us a distance or a displacement. Well, when we look at the graph, that's just taking this height, which is 8, and this width, which is 6. So we're taking 8 times 6, and that gives us 48, and that would be meters, because remember, this is in meters per second, this is in seconds, and the seconds cancel, and we're left with meters. So that area represents the displacement. So you can look at a graph and actually kind of know how far have you traveled as long as we're looking at a graph of velocity versus time. Okay, so that's kind of the core concept of what we're looking at here. Now, it's great when we're dealing with constant velocities, because everything is length times width, or it's always boxes, or I should say rectangles, so we can always find the area easy there. When we look at this part here actually is more on a diagonal. You can see that we are changing our velocity, so our velocity is changing, okay? But it's increasing at a constant rate, okay? It has a slope. And so what we do is we can find like the slope of this, and that would tell us, well, that'd be the slope of that is a topic for coming up here tomorrow night, okay? So again, we can look at this and we say, well, how much displacement did we go through in this amount of time? Well, we're going to look at it in terms, again, of finding the area of underneath this curve. Now, that area happens to be a triangle, and the area of a triangle, you may remember, is 1/2 the base times the height, okay, where my base is actually just my time, okay, and it's 4 seconds. So I'm going to take 1/2, 4 seconds, times my height, which was 8 meters per second. The seconds cancel, and I'm left with meters. So I'm looking at this, and I'm going to say, well, 4 times 8 is 32, and half of 32 is 16, so this is 16 meters. So I traveled 16 meters in that, okay? And that's kind of how we look at it. So I have my 16 meters here, I have my 48 meters here, so the total displacement that I went through on this little trip, following my velocity time graph, will be 64 meters. Okay, so again, area under the curve of a velocity time graph is our displacement, and it goes directly back to our relationship. Okay. Let's look at another situation here. So my next situation is kind of a little problem, and it's kind of a typical type of a thing that you'll see, and it's a mind-bending type question to see if you really truly understand this stuff. So we're going to say you're driving down the road, and you're traveling at a constant rate of 29 meters per second, and all of a sudden, you know, there's a cop car on the side, and if you figure out 29 meters per second, okay, you're probably exceeding the speed limit. So he all of a sudden decides to catch up to you, but he has to start from rest, okay, that starting from rest is starting with 0 velocity, and then he has to kind of speed up. So he's going to change his velocity as he tries to catch up. And we're going to say that he speeds up under a constant rate, okay, so that we're looking at something like that. If you don't change your speed at all, how fast will the police car be going when it passes you? Now, the core question here is, before we even get started, is will he be traveling slower than you, faster than you, or at the same speed as you? Okay? Now, I want you to go ahead and pause the video right now. I want you to think about this a second. Write down your answer in your notebook just to see if you can get that and if you understand it, okay? Well, welcome back, and hopefully you've got your answer written down. And now let's look at this from a graphical sense, okay? So I'm going to just do a little sketch of a graph here. And this is going to be my velocity versus time graph. And I'm going to say up here is 29 meters per second. So that's my rate, or I should say your rate. I'm not speeding. You're the one speeding. Okay, and so you travel along and you drive like this, and you never change your speed. Okay? Now what has to happen here is at some point in time, our police officer who's starting here, actually I'm going to do this. I'm going to give myself a little bit more room. Okay. This is going to be 29. Okay. You're going to drive along like this. Okay? At some point in time, that police officer is going to have to catch up with you, right? And so they're going to start at 0 meters per second, and they're going to be speeding up under a constant rate. Now, at some point in time, they're going to hit that 29 meters per second. So they can't be going the same speed as you because you'll never catch up, right? They have to go faster. So at least you kind of got that, and hopefully you got that right. But what happens here is eventually their speed is going to have to be so much greater than yours. And what we're doing here is we're looking at this and we're going to say that the area, okay, under the curve, which represents our displacement, is going to have to match. And it only makes sense. The distance that you cover from the police car to where he catches up is going to have to be the same amount of distance that he has to go through. So in other words, our areas are going to be the same. So the area of you, okay, this area, will have to match the area of the police car. Okay, and so that's really how we look at this. We look at this from an area perspective. So in other words, the two areas or the two displacements have to be equal to each other. Now, I really didn't give enough information in this problem to actually solve this one. But this is going to be your question for tomorrow. So now let's not only just say that we're going to try to figure out how fast will the police car be going, but we know this. We're going to say that it takes 10 seconds for the police to catch you. All right. So we're going to add a piece of information. So in other words, we're going to give you the fact that you're going to get 10 seconds of time. Okay, so in other words, the time that it takes is going to be 10 seconds, and the displacement's going to be the same. So in other words, you knowing the time that you're spending on the road and knowing that you're traveling at 29 meters per second, you should actually be able to now figure out, okay, we go from 0 to 10, you should be able to figure out the area under the curve for your graph, okay? And that area, which is your displacement, is going to be equal to the area that the police car is going to have, which is 1/2 the base times the height. And then you're just looking for the height. So you can go ahead, if you want to right now, pause the video. You can go through, do this calculation, write it down in your notebook. I'm going to be giving you a slip of paper tomorrow, and that's what you're going to have to put on there for an answer to see if you kind of understood how to do this question. And if you're struggling with it, then I'm going to actually ask, or I'll come around and I'll probably help and work it out in class so you can get to see how I do it in class too. All right, moving on. Maybe I wanted to look at a new graph. Okay, so now this is a position, whoa, back it up. Okay, this is a position time graph, and I wanted to look at how do we change a position time graph into, say, a velocity time graph, and look at it from a different perspective, or under this whole area perspective. So I'm going to make my little graph that's going to go like this, and hopefully I'm not writing over myself. I always try to remember that I'm right there, so hopefully I boxed myself in. This is my velocity, this is going to be my time, and I'm going to look at each of these and I'm going to try to figure out what would be my velocity under each case. Because again, under a position time graph here, I'm changing my position, okay, with respect to time, and so there's a slope, and that slope should represent the velocity. So my two values here were 30 minus 0 over 5 minus 0, and 30 minus 0 is 30, 5 minus 0 is 5, that's 30 divided by 5, which is 6 meters per second. So in other words, I'm going to travel for 6 meters per second for the first 5 seconds. So I'm going to try to parallel my graph here a little bit. So for the first 5 seconds, I'm going to go along at 6 meters per second. All right, and I'm not going to change my speed any for that 6 meters per second, because notice that it's constant, so in other words, my graph doesn't change. Then all of a sudden I hit this point right here, and this is a flat spot. Now what does a flat spot mean again on a position time graph? Say it with me. Constant position, okay? So in other words, we're not moving, we're sitting still, and we're sitting still for 5 seconds, which means that we have a 0 velocity for 5 seconds. Okay, so I'm going to bring my graph back down like that. Then I have this point right here, which is another slope, but notice it's a negative slope. Negative slope just means I'm driving backwards, again, back towards my starting position. I am going to find my slope here, so my slope is going to be, let's see, this one, so it's 10 minus 30 over 20 minus 10. Let's see, 10 minus 30 is a negative 20, and 20 minus 10 is 10, so this is a negative 2 meters per second. So now I'm down here to a negative 2 meters per second. And I'm going to travel that far for these 10 seconds. So there you go. Now all of a sudden I hit this flat spot again, which tells me I've got constant position, which means I'm not going to be moving, so I have 0 velocity. And then I have this last point, which is my 30 minus my 5, that's my time, and it's 20 minus 10, so that's 10 over 5, which is 2 meters per second. So I'm back here at 2 meters per second for the remaining part. Okay, so again, I can look at either graph now to figure out my displacement. Okay, my displacement from my origin right here to right here, 20 meters. So this gives me 20 meters of displacement. I should get the exact same thing from my velocity time graph. And I'm going to look at it from the area under the curve perspective. So again, my area under the curve is this area piece right here, which is 6 times 5. 6 times 5 is 30 meters. So I get 30 meters for that one. This one is going to be 2 times 10, or 20, but it's below this line, which is a negative, so I'm actually moving backwards 20 meters. And then I have my last piece here, which is 2 times 5, and 2 times 5 is 10 meters. So I get 10 meters for that chunk. And these chunks didn't give me anything. So now I have 30 meters, I have 10 meters, that's 40 meters. Oh,